So good evening, everyone. I hope you are well. Welcome to the Competitor's Ultimate Guide to Data Analysis for Driver Performance with our guest speaker, Ben Newman from Motorsport Performance Solutions. My name's Katie Baldwin. I'm from Motorsport UK, and I'm primarily here to monitor the Q&A and field any questions for Ben at the end. I think that's all from me for now. So I'll hand over to Ben and enjoy the session.
Thanks, Katie. Cool. Well, thanks everyone for firstly giving up your evening to listen to me talk. So I've sort of been asked to introduce people into data analysis techniques and what we do in the sort of modern motorsport industry. I chose the topic of sort of driver development because I think most people will be interested in that. You don't really have to have an engineering background like I've got to sort of be able to understand it or take an interest in it. So it's quite, to get started, it's got to be quite broad. You have got to know a lot of the technical goings on in the background to appreciate how data analysis systems work. So there are some fairly complex topics in there, but I've tried to keep it as brief as I can. My sort of intention with this presentation is to sort of introduce you all to all the various sort of buzzwords, the topics, all that sort of thing, to give you a broad overview of the subject. So even if I don't cover everything tonight, you've got plenty of terms to go away and research yourself, and to get yourself up and running with a data analysis system. And sort of, yeah, the focus is on how you would use it to improve your own driving. So there's plenty of information in the slides. I'm not going to sort of read them word for word. What I'll do, because I know this will be made available afterwards, I'll sort of gloss over the information on the page, and then if you want to read more deeply, I know it's going to be made available on the website afterwards. So that's the way I'm going to try and present it. Engineer by trade, so I don't do much of this public speaking, so bear with me. I think sort of firstly, don't like talking about myself too much, but likewise, I think you've got to assess for yourself whether I'm worth listening to. So I give a little bit about myself and a little bit about my company, MPS. So I originally got no electrical background, no computing background whatsoever. I'm very much hands-on trained, and I think mechanically, not electrically. So I trained as a race engine builder. And then from building the engines, I got involved with testing them on the engine dyno, and got interested in the electronic tuning via a laptop. I sort of wanted to progress and learn this more, so I decided to go to university, got a motorsport engineering degree. From that, I got offered a job with Porsche GB as technical support engineer, which was a nice mix of mechanical engineering coupled with looking at the log data to sort of try and visualize as many problems as we could. So that was my introduction into data analysis and really got me hooked and sort of forged my career today. I was then fortunate enough after Porsche to be offered a job with Cosworth Electronics, arguably the biggest motorsport electronics company there is. For me, it's between Cosworth and Bosch as to who the giants are. Bosch seemed to have the engine control side of the market down now, whereas Cosworth was still pretty, seemed to be the dominant force in chassis side electronics, in my opinion. So chassis side would be data loggers, driver displays, steering wheels, power boxes, that sort of side of things. So I was fortunate enough there, you're working directly with some of the world's leading motorsport manufacturers. So you've been involved in plenty of the customer racing GT3 cars and cup cars and touring cars, etc., that are still on the market today. After that, I decided I'd learned enough and got enough contacts that I could go it alone and be my own boss. So I started MPS. I started at the end of 2016, getting ready for the 2017 season. Been really fortunate to have some really great customers contact me, and we've had some pretty successful race campaigns over the years. I dabble with both systems and data engineering, as well as race engineering. So sort of highlights for me were we won the AM class of the WEC Championship with an RSR, Porsche RSR. We won the British GT Championship in Pro-Am with a Mercedes GT4. Won British GT3 races with a Bentley. My guilty pleasure is British touring cars. We've had a bit of success with that. And then some other cool projects I got invited to be involved with McLaren, both working on the P1 GTR sort of track experience program. And then I came in fairly near the end to help the guys get up and running with the 720S GT3 race car. So that's a little bit about me. Hope you deem that significant enough to listen to what I have to say, really. So to start with, before you even get into looking at log data and how you can analyze it to improve yourself, you've firstly got to collect the log data. So I want to give you a little bit of background how all this hardware and software works, just so you can get the buzzwords and sort of decide what sort of electronic sort of data logging system you require for your application. I know we've got people from all sorts of motorsport logging into this. So my experience is GT racing and touring car racing, but I know there'll be people with sprint cars, hill climb cars, trials cars, all this sort of thing. So if I give you a broad overview, you can then start to tailor it to your own specific use. If you say a lot of the more expensive, higher end racing that goes on now is what I deem as customer racing, where you go to a manufacturer and buy a car complete. So a lot of these, if it's fairly modern, will already have data logging hardware either built in, or at least the manufacturers would probably offer a sort of plug and play solution. So you don't have to get involved too much in designing and engineering the system. But so if that is you, apologies, but I think hopefully you'll still find it interesting as to how some of this technology works. If you're I'm fortunate enough to work in the higher ends of the sport with the bigger budgets, but I still just earn an average wage. So when I try and play, I'm very much at the lower end of the budget. So I understand some of the budget limitations for people that be logging in right now. So I've broken down the parameters, the channels we might want to look at into two groups. Ones which I've deemed sort of essential. You've got to include provisions to buy these sensors, to mount these sensors as part of your initial budget to make it worthwhile data logging. And then after that, there's a list of luxuries that would be even more beneficial to your driver performance analysis, but not essential. So if you allow for them, design them into your electronics package from the start, you can upgrade to them as and when you can afford. So the fundamental thing we look at when analysing driver performance, car performance on the lap, is the speed throughout the lap. So it goes without saying that you need some sort of means of measuring the vehicle's speed. The next sort of most significant parameters to look at are your acceleration that the car experiences. So lateral acceleration is side to side, sort of what you generate through a corner, and longitudinal is forwards and back. So that's your acceleration and your braking forces. The next is, it'd be easy for me to say brake pressure, but that's not necessarily true. You'll see later on in the slides I refer to the 80-20 rule. So what I've used here is the broad turn application. So we want to be able to measure what the driver does with the brake pedal and how it affects the brake system. Again, ideally that'd be like the brake pressure, but if we have other means of measuring the brake pedal travel, sort of in the majority of cases in terms of analysing the driver, that will be enough. The same thing goes again with the driver's throttle application and the steering application. So they are the main base inputs a driver has on the car when they're driving on track. The luxury parameters, again, these are ones that we aren't necessary, but they're nice to have. The first one on the list is your engine speed. So this is like your tacho on your car, your rev counter. Using this, we can make all sorts of math channels and work out where we're changing gear, what gear we should be in, things like that. But ultimately, it's not essential to get underway with analysing your driver performance. Linked closely to that is gear position, as I just said. We can, if you've got like a sequential gearbox, it's quite easy to get onto the gear barrel and define your gear position. But with a bit of simple maths, if you've got a H pattern gearbox, you can, if you do your speed over your engine speed over your vehicle speed, you can quite easily calculate a gear ratio and work from there. If you've got a manual car with a clutch pedal, it's a good idea to track how the driver applies the clutch. I mean, even at touring car level, you won't believe the mistakes that go on there. It's not mistakes, it's that a driver doesn't realize they're doing it. It's very easy to rest your foot on the clutch in high G situations. So that's a good one to watch. A real nicety is the individual wheel speed sensors. So I mentioned before an overall vehicle speed. We could do something like GPS speed for that. Whereas the real beneficial one, if you can afford to do it, is individual wheel speed sensors. So this is a speed sensor on your front left, front right, rear left, rear right. There's various benefits to analysing those, which I'll cover later on. So as I mentioned, the GPS is a way of measuring your speed firstly, but also using the coordinates. We can, if you use the GPS latitude and longitude values, which GPS systems get, you can do all sorts of other trick stuff with them to help analyze your driving on track. Also with a GPS system, it becomes really easy to be able to break your data down into laps. We can sort of put in an artificial a line across the track using GPS technology, and every time you go across that line, it signals to the data logging system that you've started a new lap. I'll cover this later, but when we look at driver data, it's really beneficial to have on our screen just lap by lap and compare one lap to the other as we analyze the data. So a GPS system is really recommended if you can get a system that suits it. And the final one is, if we're looking at the driver's performance, this is probably at the higher levels of the sport, sort of the GT3 racing, GT4 racing that I do, which has various engine maps, traction control, ABS, this sort of thing. They're all adjustable we can advise on the radio as engineers, but ultimately the driver has control of these on the track. So it's good to be able to data log them and analyze what setting they use affects the driver's performance. So yeah, in terms of purely analysing the driver, these are the parameters I would sort of recommend building into your system. But likewise, driver analysis is only part of the many broad uses of a motorsport electronics and data logging package. So if I try to talk about everything, I'll be here for hours. So I've tried to keep it condensed, and this is specifically focusing on driver analysis right now. So again, choosing, how would you choose the hardware you use? It all comes down to what your intended use is for the system. So I'll cover a few more topics regarding hardware, but you need to come up with a set of requirements, how many sensors you want to use, how you're going to, if there's all these systems in the car, how you're going to communicate with them. So there's quite, the market keeps getting bigger and bigger. There's more brands, more manufacturers popping up left, right and center. So it could be a bit overwhelming if you haven't really looked into electronic systems before. But you'll tend to find that once you sort of apply your situation, your car that you're trying to design a package for, you'll soon realize that with your certain set of requirements, there's your choices become much smaller, and you're only down to a few choices, which makes it much easier if this is the first time you've played with motorsport electronics, which I'm sure it will be for most people. Touching on that, so the modern race cars are a network of devices, electronic control systems. They've all got multiple purposes. If I highlight the dash display in the middle, that's Cosworth's ICD, which is not only a dash display, it's a CAN hub, and it's also a data logger. So you really need to think about how your systems are going to integrate, how they're going to work into the car, and then you can go from there. Ultimately, they all do the same, can all do the same job of logging data, and sort of for the purposes of analysing your driver's performance. It doesn't really matter how it's logged, as long as you can look at your squiggly lines after. But if you're going to the trouble of buying a system, it's good to also think about the whole car system. Again, that's beyond the scope of this presentation, but just to make you aware of it, that's how it fits in before you rush out and buy the first data log you see. I'll just point out at the top of the page is VBox's camera system, which is both a camera and a data recorder, which if I'm purely advising a customer purely as a driver monitoring system only, that's still top of my books. That allows you to take communications data from other systems on the car. You can also wire in your own dedicated sensors, and then you've got the added benefit of having your video and your driving data all synced together as one. So they're definitely worth looking at. But again, this is just sort of look at your car, look at your application, and realize, write down what your requirements are, and then you can build a system from there. So I've already mentioned some of the parameters. So we're talking about throttle application, steering application, all these sorts of things. So we need some way of monitoring them, measuring them. So one of the first ways, the prime way, is to physically attach a sensor to whatever we're looking at, and then wire that into your data logger. Then your data logger can process that sensor and save it in its memory. There's two main types of sensor. The first sensor we'll look at is an analog sensor. So analog sensors are sensors which can track and measure a system with a varying state. So the example I use on this slide is your throttle position. The driver can go anywhere between zero closed and 100% fully open and sort of all sorts in between. So there's no on or off, there's no 1 or 0. It's a constantly changing variable. So the way analog sensors work is they whatever you're trying to measure, whether it's a position or a pressure of a fluid, etc., like that, it'll have a set working range, and in between those two working ranges, it'll have a sensing element that will, this is 99% of the cases, have a sensing element which will change its resistance based on the input to it. So with a pressure sensor, the more pressure it sees, the higher the resistance, for example. So what we do then is we supply a constant voltage. There'll be a dedicated power supply pin out of your data logger. If we pass that through the varying resistance, we'll get a varying voltage back out of it, and then we feed this varying voltage into our data logger. And what we then do is we can calibrate a voltage against an engineering unit. So for the example of throttle position, it would be a 2.5 volts equals 50% throttle and something like that. So what we do is we end up with a calibration curve which converts voltage into engineering units. I've included a screenshot just from one of my data logger setups I had open in the bottom right hand corner, and that's actually for a damper travel sensor. You see it's nice and linear, and we follow volts across the bottom. We map that to a millimeters of travel, like a ruler. So that's broadly how they work. So analog sensors are the most common for monitoring fluid and changing states. So if you go back through the list of essentials and luxuries, you work out how many of them you'd like to measure. That will give you an idea of how many analog inputs you need on your data logger. So some come with 4 as standard, and then they go 8, 10, 12, 16. It normally increases with cost how many analog inputs you get. So if you understand how many analog sensors you need, you can then start to hone in on what hardware suits you. I've just put a little bit in here about how you wire them. Again, I probably won't cover this live during the presentation, but it's just will help you narrow down when you start looking for sensors. There's reputable brands which are motorsport proven. Motorsport's a notoriously harsh environment as it is, let alone for sensors. Sensors are getting smaller and smaller, and as that happens, they're obviously more prone to vibration and all sort of other harsh environments for electronics devices. So yeah, there's reputable brands, but they obviously charge a premium for their well-engineered products. But you can get yourself onto eBay or RS Components, like electronic suppliers like that sell much cheaper versions. So there's a few buzzwords in here if you read through that will help you to narrow down what sort of sensors you can apply in your application. So I just talk about a few types of analog sensors. These are the ones that will be, excuse me, the most common for looking at driver performance. So first thing you have is fluid pressure sensors. So in our application, this is basically going to be brake pressure. If we measure the brake pressure, we're almost directly measuring the braking force applied by the driver. So I really would advise, if you can afford to build in as part of your brake monitoring, is use a brake fluid pressure sensor. Just a few things of note. The hydraulic brake fluid can be corrosive to some types of sensors, so you have to make sure you buy one that's specifically approved for use with brake fluid. And you can see really high peak pressure or comparatively high peak pressures in the braking system. So you want to make sure you've bought a sensor which is designed for that. The most common ones will probably be anywhere, if you search for a pressure sensor, the most common ones you'll find will be anywhere between 5 and 10 bar pressure, whereas my rule of thumb is to buy one with at least 125 bar pressure capacity. So you make sure you're buying a pressure designed to cope with the pressures you're going to see. They can be, obviously, if you're a home mechanic and not particularly confident, the idea of cutting into your braking circuit just to put a sensor would probably be quite daunting, but there are nice ways of doing that which are very reliable, very safe, and proven and used day in, day out. So the two real options are to break your brake lines and build in what's called a T-piece. So your fluid will carry through there as if the line was always there, and then it feeds pressure up to your pressure sensor here. The other way of doing this is if you've already got established brake lines, a braking system that uses a banjo bolt to either connect to the master cylinder or other joint in your system, you can get these extended called double banjo bolts, which allow you can essentially break into the circuit and add your own specific line, which would go to a brake pressure sensor and nothing else, without the need to modify your braking lines that are already there. So there are a couple of options. Say it sounds quite daunting if you're not too mechanically minded, but if you do it properly, they are safe and proven, and it's what the majority of the customer race cars you see are driving around with at the minute. The next type of analog sensor is a position sensor. We actually looked at one of these in the calibration curve I showed you a few pages back. So they're basically just a telescopic measurement device, a bit like an electronic ruler, if you would, and they just track linear changes in position. So you can, in our application for looking at driver's inputs, you could build one of these and mount them to your pedals. So okay, your pedal rotates around a point, it's got a pivot, it moves through an arc. It won't be entirely linear, but as we will discuss later with the 80-20 rule, we only, in most cases, you only want to see a general shape. So you could use this to track pedal movement. You could use this to track your actual throttle butterfly movement. And another way of using these for driver analysis is if you mount it onto your steering rack. So there'll be parts of your steering rack that move linearly, and then with a bit of a simple calibration process, you can turn this linear movement into an angular change of the wheels. So they're hugely useful, they're relatively cheap, they can be quite easy to mount. So again, they're worth considering. Another two types of analog sensor which are common are rotary position sensors. So these rotate around an axis and you calibrate to an angle position. So if you imagine with steering, your steering wheel, that's a circle, it rotates. So that moves angularly. So these can be a great way of monitoring your steering angle and how the driver uses a steering wheel. The top right is an example which I've used, where you use a small drive belt which connects your steering column to the sensor, and it follows your steering inputs. Another way of quite quickly, easily, relatively cheaply, and this is probably my favorite for unintrusively, so no permanent modifications, can all be removed, is to use a string potentiometer. So particularly favorable if you're working with a road car, predominantly road car, just to do a bit of track days, etc. like that. You want to install some sensors, but you don't want to be drilling holes in your nice dashboard and affecting the resale value. So string potentiometers are a bit like a retractable washing line or airline. All it basically does is tracks the string's movement. It's slightly under tension, so it tries to return. So you could use leads to follow a pedal throughout its movement, as long as it doesn't block your foot. Or another common use for leads is to wrap the string a few times around your steering column. So at full lock, the string is fully wound round, and then as you remove and add steering lock, the string will rotate and unravel around the steering column, and that way you can just track the steering wheel movement. So you've got quite a few options to integrate and mount sensors into your car's mechanical package. So hopefully one of these will suit you. Say there's no real right or wrong. They all serve a different purpose. So it'll be very much dependent on your situation. So the other type of sensor that will be commonly used in motorsport is what's called a digital sensor. So whereas an analog could provide monitor a varying state, a varying system, this one is very discrete and only works in ones or zeros or ons and offs. So before we had a wiggly line for the analog sensor, this one is step changes, ones or zeros. So in a motorsport application and in our application of monitoring the driver, this will typically be used for speed sensors. So the way these work is they're all based off a magnetic field principle, and we use that to detect the metallic ferrous part of a trigger wheel of some sort. So this could either be mounted to the engine at the crankshaft, which rotates, or somewhere around your drive shaft, or at your hub somewhere on each of your wheels. What we do is design these trigger wheels, which basically feature gaps, and they have teeth which you see and a space which you don't see, known as the gap. And what we can do is, if we know how many teeth there are on a wheel, I think this one's probably 36, so 360 degrees divided by 36, you've got 10 degrees between each trigger. We can count these pulses we see, these step changes in the digital signal, and from that, with a bit of maths, we can work out the angular velocity. And if we then know the physical circumference of, in the example of wheel speed, if we know the circumference of your tyre, we can then quickly use that to work out how far we've travelled, and moving on from that, we can get a common speed measurement, whether that we translate that into miles per hour or kilometers per hour, etc. So this is just a little bit of background how digital speed sensors work. So in our application, most of the other sensors would be analog sensors, and then if we look at engine speed or we look at wheel speeds, these would be digital sensors. The reason I mention the differences are because likely your data logger hardware will be handling the different types of sensors differently. So they normally have an amount of dedicated analog sensors and an amount of dedicated digital sensors. Digital are probably harder to come by. So if you imagine you need to, you want to log your engine speed and also all your 4 wheel speeds, that's 5 digital inputs you need. And if you start looking up data logger hardware, you'll see that's not particularly common to come by. So that will quite quickly narrow down any hardware choices you have to make. I touched on this briefly. So GPS technology, it's now commonplace in our everyday lives. Our smartphones have it, and probably most of our cars do. I won't go into too much detail on the slide, but it uses a series of satellites orbiting the Earth to communicate with, and from that it can accurately calculate its position on the Earth's surface. So what we can do there is the world's broken down into latitude and longitude lines. We get values for both. And you'll see later on in the presentation, we can use that to our advantage, namely to map out the driving line, and also we can use this for triggering the start of a new lap as we drive around the circuit in our lap after lap. So I'll let you come back and read the information here, but say GPS sensor technology is hugely beneficial, and I would really recommend getting a hardware solution that works with it. So the previous few slides were talking about if we want to add our own physically add our own sensors to the car to monitor our drivers' inputs on the controls. So another big part of modern day motorsport electronics and data logging is communications. So depending on the age of the car you're working with, obviously, it will presumably have some sort of electronics control module already installed on it. So the common one most people would have know of in motorsport circles is the term ECU, an engine control unit. That might already have a throttle angle sensor as part of its system. It'll probably have the engine speed, of course, too. So that's a few of your wish list for analysing the driver already ticked off before you've even put a driver specific data logger in there. So it'd be pretty wasteful, pretty pointless to install duplicates of that. So communications protocols are commonplace amongst electronics modules to share this sort of information. There's a few different types of communication protocol that would be employed in the motorsport system, but the most common one, the one that I would focus on if you're just getting into it, is a system called CAN. This is common in both motorsport electronics as well as road car electronics. Unfortunately, I'll go on to explain a little bit more, but in automotive applications, the CAN bus is a little bit more trickier to try and interface with. So CAN communications is, if you're not very experienced, it's probably only really realistically possible if you have other motorsport level devices already installed on your car. So if your engine tuner has already put an aftermarket ECU on, etc., the CAN protocol and CAN communications is relatively easy to set up from a motorsport device. Whereas if you're trying to interface with BMW's latest CAN bus network, it gets a lot more complicated a lot quickly. So I'll just introduce you to the term. It's something to look out for, and it'll be something for you to research as you look at your own application. I've put in a few more slides as to how CAN bus works, because I've had sort of a conversation with a few customers previous to being asked to produce this presentation. It's, oh, well, my road car's got CAN, can't you just interface with that? So this is, the answer is technically yes, but it's hugely complicated. So I've included this information so you can sort of start to read up on it, start to learn some buzzwords to go off and do your own research. But fundamentally, the way a CAN bus works is it sends around what we call packets of data. They all have different identification numbers, so you don't clash and you don't get a contamination, if you will, on the CAN bus. And there's a huge amount of available identification numbers you could choose. And then once you have a CAN packet, there's a large amount of possibilities of where you could hide your data within this CAN packet. So if I'm trying to make my ECU send me throttle position, for example, there's an almost infinite amount of possibilities it could be hiding on a CAN bus system. So if I don't know where the ECU is sending it, it's very, very difficult for me just to rock up with my data logger and try and decode it. There's no hard and fast rule. So yeah, in theory it'd be nice just to, well, my car's already got CAN bus, can't I just use that? In practice it's a lot more difficult. So I won't go through too much more of that during this presentation, but there's a bit of information here you can go back through and sort of read on your own time. Yeah, this just follows up the previous slides. But say CAN is a great tool if you're already in control of some of the other electronics modules on your car. So I know plenty of people that have started to tune their race engine, gone to an aftermarket tuner, got an aftermarket ECU on there, and if you're in control of that side of it, CAN bus is a great tool and a relatively easy tool to use if you're trying to integrate a motorsport data logger. But it's just a bit of a beware. If you're trying to put a motorsport data logger into a largely road car based platform, it can become very difficult very quickly. There's a bit of information on this slide about how an automotive CAN bus system works. I'll just take a few key points from it. So the CAN buses in road cars are hugely safety critical in many applications. So they are protected very, very well. There's lots of safety systems in there. You imagine you don't want to accidentally send a 100 when you're meant to be requesting a 10, for example, if you're going from the driver's throttle pedal. I mean, that's an extreme case, but that's as serious as it could get. So yeah, the safety implications could be dire if they're not thought out, especially with a car that's used on the public road. So there's a huge amount of time, money, and investment put into safeguarding the communications bus in a road car, and therefore it becomes very, very hard to interface with. It's not impossible. I've done it for manufacturers and that side of things, but it is hugely time intensive and you need some special equipment, and the be all and end all of it is it comes out the realms for Joe Blogg's motorsport enthusiasts to work with their car. So I mean, there will be, if you're say a BMW M3, for example, which is a hugely tuned car in the world, there's many tuners, there's many specialists that they may well have deemed it sort of financially viable to spend the time reverse engineering a manufacturer's CAN bus, so that information is sort of readily available for a relatively small cost. So I wouldn't give up on it, but just beware. It's a difficult thing to do, especially if you have no prior experience. There is a nice, easy to work with communication protocol in road cars now. I believe it's 2001. Don't quote me on that, but UK petrol cars had to include a thing called an OBD2 port. You might be aware of it as your diagnostics port. So this was mandated by governments as a means of a standardized way of communicating emissions specific channels, data channels. So as it's standardized, there's many products, there's many manufacturers of products that will work with the OBD2 protocol. So there are plug and play solutions to get some data from your car using an OBD2 device. Unfortunately, with our application here of wanting to monitor and improve a driver's performance on track, they only really focus on engine channels, engine parameters. So it's a great simple solution for us to grab the engine speed and your throttle position, but it won't offer us a solution to monitor the driver's input on the brakes or the steering angle, for example. So now I've talked a bit about the various inputs to collecting driver data. So the sensors you need and the specifications you need to look out for, buzzwords you need to look out for when you select a data logger. So hopefully I've given you enough information there just to whet your appetite to see what you need to look for. So this next stage is assuming when you've bought a package and you've collected your driver data. This is now how you would analyze it. The first step when you analyze your data is you need a sort of a thought out, a well-defined, what I call a worksheet, others people call a workbook. This is a collection of graphs and data displays which are thought out and are for the purposes of what you're trying to achieve. So I do this professionally. I don't just look at driver, I look at engine reliability, gear shift quality, suspension data, car performance channels. So I have a number of worksheets built into what I call a workbook, and each one is created with a specific purpose. So I might, if I'm looking at gearbox, for example, I'll be more channels I'm interested in related to the gearbox that aren't applicable to anything to do with driver analysis. So the worksheet contains a collection of channels and displays, and those channels, if it's a good software, good data analysis program, you'll be able to calibrate the properties at which you display. So I'll go backwards and forwards between slides. So this is a screenshot from my driver analysis page in my workbook. So this is for a Bentley GT3. So it's a GT3 car. It's smothered in sensors. We're very lucky there that we've got all the toys that I'd possibly need to be able to analyze the driver's data. So the simple this would be mostly made up of the essential channels which I talked about. So we've got speed, steering angle in blue, throttle in green, brakes application in red. These are the sort of the bare essentials I would deem if you want to look at your driver's performance. Already I've played around with the scales, so we call it the y-axis. I've set, so the throttle could be anywhere between 0 and 100%, so I've only focused in 0 to 100. I've tried to give space on the screen based on how much resolution I require. So in general with throttle, you don't really care too much whether that's 48 there or 49.5 there. You're looking at general trends, so I don't need to give too much screen real estate to the throttle, whereas speed, the one in white, is obviously hugely critical. And if I can gain another 1 or 2 Ks in a corner, slow speed corner, I'll be really happy. So I give that a bit more screen real estate to try and improve the resolution. So I think that's what I talk about on the previous slide. Again, a lot of this stuff is probably worth mentioning is there's no real industry standard for any of this. So there's nothing that says, oh, you need to use this color here, or you need to lay out your channels in this format. It's very much personal preference. There's something which seems logical to yourself. So what I might find useful may not necessarily apply to you. I've got a simple color coding. Green means go, so that's throttle, and red means stop, so that's brake. But yeah, there's no other real logic to it than that. So unfortunately, this Bentley is littered with sensors. So I've got all the luxuries as well. So if you see the next sheet, it's a duplication of the type of graph. There's another time distance graph which I'll talk about shortly. But this time it's filled with just wheel speed sensors. So you'll see I've got each corner overlaid on top of each other. So it makes it really easy for me to see when a wheel locks up, for example, like this green one here, or if you're struggling for traction, like you see the pink is going faster than the blue down here. So the way you sort of strategically lay out your data analysis will save you dividends in the long run. It'll make it that much easier, that much quicker for you to delve into analysing the driver performance. I'll just explain, I haven't covered all of this in the rest of the document because you sort of had to pick a point where I stop, but I've got down the left hand side, I've got the various driver aid settings I've talked about. So we've got ABS, engine mapping and traction control down the side, and also at the top I've used what's called a bit indicator. So each one of these coloured squares is a bit, it's 1 or a 0, on or off. And Cosworth stuff is quite tricky, and you can do sorts of various cool things with it. And one of them is you can log how the shift lights are working. So these are mimicking the shift lights that drivers see in the car, and you can see all of them are illuminated, so they've all got a different color. The colors match the LEDs I set in the car. And I've just paused the cursor here. So this white line with an X is the live point which we're looking at, and it's at the end of the rising engine speed trace in blue. So that basically means we've come to our shifting point, and you'll see the next few data samples working from left to right that the driver has performed a gear shift. The gear's gone up and the engine speed has dropped. So that's just a brief introduction, but this is how I like to set out my driver page. The key point here is to just make sure everything's clear, everything's easy to read, and you give yourself the best possibility of sort of noticing any irregularities, and then being able to focus on some of the specific points I'll bring up later on in the talk. So I touched on it briefly before, but the time distance graph is sort of your friend here. This is the one you'll be looking at most, you'll spend your most time looking at, especially when you're looking at driver data. So a time distance graph, it has, as its name suggests, on the bottom, which is called the x-axis, you can either choose time or you can choose distance. So working from left to right, your data traces from the various different sensor readings we've got, they chronologically move as you increase whatever you use as the x-axis. So if you're looking at engine data, for example, it's probably much better for you to analyze this with respect to time. Most an engine's measured in revs per minute, etc. So there's the time link. Whereas if you're looking at a driver data, I often find for nearly every case you're trying to consider, you're much better to look at your data with respect to distance, and that's distance around the lap. So I've got a bit of data up here from the Paul Ricard circuit I've just come back from. So the reason we do that is because generally speaking, I mean, there are exceptions here, but generally speaking, turn 1 at Paul Ricard will always occur at, I don't know, 540 meters into the lap. So if you want to analyze yourself to yourself, or analyze yourself against another driver in your car, etc., you've got a constant in your data, which is turn 1, give or take, always occurs at the same point. So if one driver is braking too early in comparison to the other, or one's too late to turn in, etc., you have this distance measurement that you can reference on track. So the reason I say figuratively speaking, and just to be slightly careful, is this distance is calculated based on your vehicle speed. So it's quite easy for a driver to drive around the same circuit but take a different line, and before you know it, a few different lines or a lock up somewhere and you run off the circuit, you've covered a different distance than you would have on a previous cleaner lap. Likewise, if there's a big difference in driving line, you could easily travel, one driver could travel a further distance than another. So you have to take the apex points, the braking points, with a pinch of salt if your drivers are massively different. But I say in most cases, I find a driver will quickly settle into driving the same driving line, and therefore you can trust the distance measurement. So if you see that one driver A brakes sort of 15-20 meters before driver B, you know you've got at least a good 2 or 3 car lengths difference in braking point, and you can communicate that to the driver that they can brake significantly earlier. If there's only a difference of 2 or 3 meters, I'd be much more cautious about encouraging the driver to brake later, for example. So that's just a bit of a heads up on using distance. But as I say, for driver performance, you have fixed lines in the sand if you use distance to be able to accurately compare and repeatedly compare yourself throughout the same corner or the same point on the track. I'll just go back. I think I've covered everything there really. So it's just a bit of a safety heads up. If there's only a few meters difference, I wouldn't encourage a driver to brake any later, purely based on the distance measurement. But if there's a significant 10-15 meter gap, you could say with relative confidence that it is possible, it is safe for your driver to brake later. So yeah, that's an introduction to time distance graph. There are many other types of graph you can use in modern motorsport data analysis packages. I can't cover them all here. I'll touch on 1 or 2 more, but say hopefully this whets your appetite to the possibilities of reading log data. So again, just to sort of recap, you read the data moving from left to right. You generally want to make sure everything's visible. So the reason I say that is if a lot of data analysis software, if we were to put sort of 5 or 6 different channels, so your brake channel, your throttle channel, your steering channel, a lot of them default to what's called overlay. So to me, it just looks like a mess of lines on the track. They're all overlaid on top of each other. Whereas this example I'm showing you here is what's more commonly called as tiled. So each channel has its own fixed space on the screen. They don't necessarily overlap, and so you haven't got lines on top of lines. You're not struggling to decipher what line's what. But again, there's no industry standard. There's no rules that say you have to do it like this. This is just from my experience. This is the easiest way of doing it. The other thing I would just also reiterate is a lot of data analysis software, when you first load in a channel, so say your speed channel, it sets the limits of what you see on the y-axis here. So this is a good example. We've got the speed. We've got a range here of, if I was to follow this line across, if the car ever did 0, so when it stops, this white line would drop down to 0. So it sets its limits of this display area. Most of them default to what's called auto scale. So it'll go through the data and find the maximum value and the minimum value, and set the display up according to that. Not really an issue in isolation of a lap on itself, but if you were trying to back-to-back compare 2 drivers, obviously there could be significant differences here. So what I tend to do is fix the range of in which you can view the data myself. So each time you load it up, you know where you are with it, and you're not constantly adjusting your scale to suit the particular data you're looking at. So yeah, I would recommend tiling your data, and I'd also recommend coming up with your own limits for how you display the data rather than let the software auto scale. How you come up with those limits is to do as the automatic software would do, is to open up your whole data file and go through and work out what you expect your maximum value would see, what your minimum value would see, and choose an appropriate value based on that. Some things that's obvious. So if you steer an angle, you might only be able to go half a turn lock to lock, so minus 180 degrees to plus 180 degrees if you're looking at steering wheel angle, and throttle, we can only really go from 0 to 100, but say speed, for example, or brake pressure, you have to sort of go through your data and see what limits you're working within. So a next type of a graph we see and would commonly use in driver performance analysis is what's called a split report. So not all software, but so this is from PyToolbox, which is my favorite data analysis package. It's produced by Cosworth. PyToolbox was developed back in the 90s when F1 was a bit of a free-for-all electronics wise. So it's had a great amount of very clever people, great minds have had their input as to how they'd like to visualize data, etc. So it's very well thought out, and as a motorsport engineer, it makes my life very easy. So again, Cosworth has a brand name associated with it, so there is a cost there. So I realise that's not applicable for everyone, but say split reports aren't just common to Cosworth; they feature in other brands' software, data analysis software too. So it's definitely worth bringing up. So a split report basically allows you to break the lap down into a number of different splits, a number of different sections. You can, if you're familiar with TSL timing, etc. in the UK, you'll know they normally break the lap down into 3 sectors, for example. So you could quite easily break the lap down into 3 sectors. What I tend to do is try to break the lap down into corner segments. And I say the word segment because you have to be careful to ensure that you pick segments of corners which can be classed as independent corners on their own. What I mean by that is, take a chicane, for example, Knickerbrook at Alton Park. You've got a right, left, right. If you broke that down as to 3 separate corners, you could quite easily kid yourself by going massively fast through one to get a good sector time, but completely compromise the following corner by going in too fast to it, and therefore you get one nice quick looking sector, but your rest of your lap is completely hindered by it. So I do my best to break it down into the lap down into individual corners, which can be treated in isolation. Once you've done that, you can then look at each individual sector and work out how the driver's performing. So this particular example we've got here from Paul Ricard, the driver's best sectors are highlighted in blue. So we've got there a 5 laps, 6 lap spread of when the driver done their best sector. So that suggests they aren't being particularly consistent with their driving. I mean, I haven't checked, but it could only be by a few hundredths, which isn't too bad. But if the significant differences, that would be a first check to say a driver needs to work on his consistency throughout the lap. The other good thing with these split reports is you can build what's called a theoretical fastest lap and also your fastest rolling lap. So theoretical just takes your best segment from each and builds them together to work out what your lap could have been. I mean, it can be useful on test days, etc. If you have a good lap and then catch traffic at a particular corner, but it can be sort of slightly kidding yourself if you say, well, I've done a 55.7, but my theoretical was a 54.3. I wouldn't count that as a driver's ultimate performance. Whereas if we look at fastest rolling lap, that's just any combination of consecutive sectors. So that is in isolation, that is a complete lap of the track, but it might not necessarily start from your conventional start finish line. So to me, that's a lot more representative of what a driver is actually capable of. Although, say, theoretical fastest lap is also a good metric to look at driver performance. Split reports are also particularly handy, speed up the process if you're just a driver in isolation driving your own car. So there might be, you come to a track and you're not sure if you've got two lines for a corner, or if you've got a choice of two gears, example, you're not sure if you can do if you can try both options a few times whilst you're collecting your data. You can quickly and easily see what one's better just by looking at that sector in isolation. So you might find that you do your best lap, you got a headline time of a 55.7, you look at your best lap, but actually you could have gone three tenths faster in turn 4, for example. You can quickly refer to this split report and say, right, I need to look at lap 57, which is my fastest lap, but lap 52 was where I'd done sector 3 best. So if I just look at lap 52 in comparison to my best lap, specifically at corner 4, wherever you went faster, it just sort of speeds up your data analysis process and allows you to quickly choose where to spend your time looking at the data, because there's so much of it. You could quite happily spend hours, and before you know it, you've lost your day. So I really recommend using a split report, and sort of, if you can afford it, buy a hardware and software package that produces it. Another type of data analysis graph is what's called an XY graph. So what we do with an XY graph is we put a channel, we put two channels into a graph. So we have one represented on the x-axis and one represented on the y-axis, and then it plots for a given sample point. It plots both values with respect to each other on this graph. So this channel, what we're looking at on the right is a zoomed in part of an XY graph, which has a GPS latitude and GPS longitude on it. So practically what that means is this is how GPS tracking works. It's laid out the driver's route around the track. So it's essentially drawn a track map for you. This is particularly useful in this situation where you've got I'm looking at two different drivers here, one's in red, one's in green, and there we can easily see differences in driver lines. So we're looking at the end of after scene at Paul Ricard here. So we've got a long sweeping fast right-hander into a left-hander. We can see that the red driver has taken a slightly wider line through the double right-hander in comparison to the green driver. So this is as another way of quickly representing your driver line, particularly useful if you haven't got an onboard camera. But this isn't the only use of XY graphs. I'll show you later on. It's good for visualizing sort of grip, or sort of pseudo making a grip circle. So it's got a number of good uses, but this is one of them, especially if you've got GPS latitude and GPS longitude data. So I've covered a few of the different types of displays you could use to visualize data. So we're now going to move into the techniques to analyze the log data. There's in many walks of life, there's the 80-20 rule, which sort of says that you can get 80% of the benefits with only sort of 20% of the hard work, so to speak. And in driver analysis and driver data analysis, that is no different. What that means practically is we can do an awful lot of work in analysing the driver's performance simply by looking at both the shape and the timing of the driver's inputs on the controls. We don't necessarily have to look at the absolute value of the channel we're looking at. So there's, but we can learn a lot from the shapes and the timings of them. So as we move forward, looking at how you analyze the data, we can break the corner down into 4 different segments, and then consider those sort of segments in isolation. Although you have to also be aware of that your performance in the previous section will affect the following section. So you can't purely just focus, you can't just take that as gospel as the particular section you're looking at. You have to consider entire corner in isolation, but there are different techniques we can use to look at each different section. So we've got my wonderful hand sketch here. We've got, as we enter the corner, we've got the braking phase of the corner. We've then got the corner entry. We've got the mid phase, the apex part of the corner, and then we've got the corner exit. So I'll try and break down each of those sections and what we look at the data in each of those specific sections. Say the first phase of the corner is actually the braking phase. This is probably where I spend most time when working with drivers, is looking at the brakes and the brake application. It's probably the most unintuitive for most common drivers to quite get their head around the techniques involved here and the science behind it. When we look at the braking phase, we can then actually, so we've got 4 phases of the corner, and the braking part, the first part, actually can again be broken down into 3 separate phases. So I will try and run you through each of those phases. So the first one is stage 1 of the braking phase. We call this the initial hit. So on the left, we've got, this is actually brake pressure data, but if you were, obviously pressure is related to the driver's application of the pedal. So in my experience, you don't get quite as much resolution. It's not quite as clear, but you would see something similar if you monitored the brake pedal position. Again, pressure is my preferred in this case, but you can also make good gains. It will be of reasonable benefit if you can't measure pressure to monitor the brake pedal position. So the first stage of the braking is to transition the car from accelerating along a straight into decelerating, getting ready, reducing speed to make the car ready for the corner. What's happening here is dynamically is the car will be, if the car had been accelerating, so it would be slightly, the load transfer would be slightly on the rear as the car squats and accelerates. And then we're asking the car to go from an acceleration state to sort of going back through 0 and then to move to a decelerating state. So what that practically means is, in the science point of view, momentarily we can put a huge amount of energy into the braking system and not overwhelm the tyres, not cause lockups. So, and this is because we are reversing the polarity of the momentum of the car from accelerating through to 0 to decelerating. So we get this initial peak, this initial spike, which we can utilize, we can gain extra performance if we utilize all of it when the driver applies the throttle. So again, using the 80-20 rule, the width of this is very hard to calculate sort of dynamically. There's a huge amount of complex factors which are always changing. Track conditions change as brake conditions change, tyre conditions change, etc. So it's very hard to say you need to get up to 98.2 here, or otherwise you're not maximizing your braking performance. That's not really what we do, but we look to make sure we have this shape. First, we have this shape in our driving, and then through sort of iterative testing and data collection, we can sort of quickly work out sort of rough values, rules of thumb as to what we expect this peak could be achieving. So again, I talk a lot about shape, brake shapes, and most engineers will. That's what we're looking for when we start to analyze our data. When I've worked with a lot of amateur drivers, what we typically tend to see is this peak, the highest point. So we expect to see the highest brake pressure, highest brake applied force should always be in this first phase. Generally what happens is the driver is particularly confident approaching the corner, so they brake lightly, which would give a lower value here, and realize they've braked too early, so that they don't apply much brakes, and then all of a sudden they're 10, 15, 20, 30 meters close to the corner, then I realize, hang on, I haven't slowed down nowhere near enough as I should have by this point. And we'll see this pressure rise. And what will happen there is they typically have the highest brake pressure just before they reach the corner. And dynamically, that's all wrong for the car. You've got all the weight transfer at the front, the front tires are overloaded, the rear's light, and you've already massively compromised your performance in the corner before you even got there. So the key thing is we should see an initial spike, and also your peak pressure should occur in this initial phase. Once we get through this initial peak and the pressure starts to back out, we then move into the second phase, which I call the mid phase of the braking. So now the car's sort of a lot more stable. It's already had the massive acceleration change applied to it, and now all we're doing is just trying to scrub off speed as we approach the corner. So the car's a little bit more settled, and it feels a little bit more controlled for the driver. What's happening here is obviously you've got amount of driving down the straight, you're storing kinetic energy in the car through speed. So as we start to brake, as the speed comes off, this energy, kinetic energy, goes down, and therefore the resulting amount of brake pressure or braking energy you need also goes down with it. So what we should see in this phase is sort of as steady as we can get, a gradually but fairly linearly decrease in brake pressure as the car just loses more and more speed. Where you, again, it's very hard to calculate exactly what number you want to see here, but there are techniques you can use with sort of other sensors to make a very good educated guess, if you would. Firstly, you've got your longitudinal acceleration input. So you want to be trying to decelerate the car at the greatest negative G that you can. So through some iterative testing, you can work out what sort of values of longitudinal deceleration your car and the track you're on and the brakes you're running, etc., realistically what they can achieve. So if you've seen higher peaks before and you're not up to this, you can come up with a number for yourself as a bit of a target. The other way of doing this is if you've got individual wheel speed sensors, which I'll cover on the next slide. Generally, it's a big generalization, but a tyre will keep giving braking grip, keep giving braking grip, and then it'll go sort of, it'll have its peak and then it'll quickly drop off and then lose grip. And at this point, we can visualize that because the wheel will start momentarily locking. So as it loses grip, the wheel will start to lock. The brake's more powerful than the grip the tyre's given, and we can visualize this. I've got an example here. Is the blue and the green traces blue and the pink traces just start to drop away. The values drop away from the actual speed of the vehicle, which would be the green or the red. So there you're at your locking limit. Say I haven't calculated it, but I'd guess there's only a few percent it starts to lock. So you could guess somewhere before that is very close to that would be what your peak amount of brake application would be, whether that's pressure, whether that's pedal travel, etc. You know, right, at this point I'm probably pulling 80 bar, so 76, 77 bar would probably be my target for this point in the braking phase. So with a bit of data collection, you can quickly map out what the physical capabilities are of your car. And then if you aren't, when you look at a lap in isolation, if you aren't matching these targets, matching these limits, you can quickly suss out an area of improvement next time you go out in the car. So the third stage of the braking phase is, it's actually spelt wrong on my slide, is the trail phase, and this sort of links in as well with the second stage of cornering as we transition from braking to steering. So there's a bit of an overlap here, but it's good to consider the brake application in isolation. So this third phase is the first two were about their main priority was to slow down the car, whereas as we reach the third phase, it's much less about slowing down the car and actually controlling the load transfer across the car. So we're significantly less brake pressure than or brake application than we did earlier in the corner. And all that's doing is just making sure the driver has control of keeping weight slightly on the front, keeping load slightly on the front. We do this because obviously the wheels steer. So the more load to a point, obviously there's all trade-offs. The more load we can keep on the front of the car, the more steering, cornering grip we get. So yeah, we're generally looking for this graduating slope throughout a braking phase, and if you're not even doing that, which I suggest most of you probably won't be, if you've never looked at this sort of thing before, just getting your shapes right will make a huge, I'm sure will make a significant difference to your lap times and your driving consistency. So the phase two of the corner is sort of just touched upon, is it overlaps with the trail brake part. And this is where the driver starts to steer the car towards the corner. So as you see before, the driver should be doing all the heavy braking in a straight line, which is what most of your instructors would have told you if you ever had instruction. But actually now we're not significantly slowing the car with the brakes. So it is possible, and it is beneficial to start to turn into the corner with some brake application applied. Again, we're looking for shapes, we're looking for timings. You should start steering as you transition into the trail part of the braking phase. So as you see here, the steering angle starts to increase, and that should be sort of steadily and gradually increasing, and we should reach the peak steering angle, which moves us to our next phase, the mid-corner phase. We should just be reaching that just as we've finished removing all of the brake pressure. So as we start to put more steering lock on, the brake pressure should be coming off, and that'll just give the driver a nice amount of control over the load on the front, whilst also maximising the amount of available grip, which we'll touch upon when we look at tyre friction circles later. So we've looked at the turn-in phase. We now got the mid-corner phase, which is, as I say, it should be the peak amount of steering lock applied. The driver should have just come off of released the brakes. We'll see in the traction circle later that the most amount of grip a tyre can give is without any, or in most cases, without any longitudinal loads applied to it. So momentarily in the corner, there's neither brake nor throttle. The driver's requesting the most amount of lateral grip from the car, and so at this point we should see the lowest speed within the corner. If any of these, if you aren't, I suggest most of you when you log this stuff won't be doing this, you'll be out of phase, so the timing will either be wrong, or you'll be doing a combination of things in the wrong order, etc. Just using the 80-20 rule and going back and just making sure you've got each section in isolation will I'm sure will give you huge benefits to your driver performance. Just one point to note is we talk about a lot the apex of the corner, especially if you do a track walk, etc. So this is the part you want to be clipping. It's just by a cone, it's just by a curb, etc. The apex doesn't necessarily have to line up with this mid corner point. It doesn't have to line up with your minimum point. There's plenty of corners in the UK where you're driving, you've already done the significant steering, you've reached the mid corner, and then the point which you call the apex on the track is where you're actually trying to accelerate and clip on the way out. So it's I mean, in some cases it is, but it's important not to confuse the mid corner phase with the corner's apex. So now we've got through the corner, it's now time to start accelerating out of the corner, and with that we sort of bring in a few more channels of data which become relevant. So we're accelerating, so obviously we've got the driver's input on the throttle, and then we can also, if we're looking at throttle, we're looking at traction, and then again the wheel speeds become more relevant. So the timings for this phase is we shouldn't be applying the throttle until firstly, till we know it shouldn't be coming off. So what you're looking for in a throttle trace is one that starts to increase and never drops back down. So it should always be increasing. It doesn't have to be linearly increasing. It's dependent on the core geometry, etc. There's no hard and fast rule there. But the general trace is once you start applying the throttle, you should never take away throttle, whether that's take away to 0 and then pick back up, or whether it's just a momentary drop. And you shouldn't be applying the throttle until the driver has sort of reached peak steering angle and is starting to come back down and remove throttle. A good way someone's told me about sort of visualizing that is if you've wrapped a piece of string around your steering column and linked it to your throttle pedal. If the string's full of tight with significant steering lock on, you shouldn't be able to press the throttle pedal until you start to get some slack in the steering. So that's what we're looking for. Is the common one, and quite often you'll get drivers complain of specifically corner or mid-corner or corner exit understeer, is where the car hasn't finished turning yet, so you're asking a lot of the front wheels, but the driver has already picked the throttle up. It's probably the most common thing I see, especially working with amateurs. And all that's happened there is the car's still trying to turn, the front corners are still trying to create a slip angle and get some cornering grip, and then all of a sudden, as soon as you pick the throttle up, the car will naturally squat, transfer the load to the rear, and now the tyres which hadn't finished cornering in the first place have now got less load on them, they've got less available grip, and the understeer just builds. So that's very common, and I would, if I could say what would be the most common thing I see is this out of sync, out of timing combination between throttle pickup and the peak steering angle. So that's why they're essential parameters for me. Obviously, we've got the luxuries of wheel speeds here. So as you can see, we've got blips of the pink one's a rear wheel speed, and so is the yellow. This is a rear wheel drive car. See, as the driver's applying the throttle, that it starts to break traction. This car has actually got traction control, which is why the engine power will be cut here. You can't see that with the data traces I've got, but this is an example of what it would look like if the car is breaking traction through to excessive use of the throttle pedal by the driver. It's also good to monitor your longitudinal acceleration at this point, because there is actually, it depends on the number of factors, but a small amount of slip, a small amount of tyre slip is actually, in most cases, will be the most beneficial to maximising your longitudinal acceleration. So again, collect some data, try a few different things. You can quickly work out what amount of slip gives you your best longitudinal G. So I can't give you numbers, so I can't say you need a 1.2 here and all your answers are all your goals are set for you. It's very much the case by case basis. But if you've got a data logger system, you can go out and collect data, a bit of time analysing it. You can quickly work out what your applicable targets, what your practical limits are for your given setup. So we've talked about sort of all the phases in the corner now, what you're looking for when you first start analysing your driver data. There are cases where you could have very good technical looking shapes. The shapes are nice. They're all time aligned, so you do it in the right order and you don't start one before you start the other, etc. But the driver is slower than someone else in the car, and that's because they're not maximising the amount of available grip they've got. So technically everything's right and they're doing it well, but they're not maximising the limit. So they're not applying the brake as fully as they could, or they're not. They could shorten the time from throttle pickup to full throttle, or they could have a few more Ks. So when they release the brake, they've got the right shape, but they could have released the brake slightly earlier and therefore carried another 1 or 2 K through the corner. It's very, the hard bit is working out where those limits are. Again, there's no, especially with the data analysis software and hardware we have available to Joe Blogg's motorsport fan, even at professional GT racing, there's no magic number or no magic sensor that will allow us to accurately calculate the amount of grip we have and therefore how close we are to the grip limit. There is a technique though we can use to actually sort of not an educated guess, but we'll get ourselves quite close as to whether we're pushing that limit, and that's sort of through the law of averages, through the law of data collection. So what we know from up top left here is the tyre grip circle, is sometimes called, or a traction circle. Is what we know is if we have just a pure longitudinal force, this is the amount of grip a tyre would have, and if we've lateral, and if we've got longitudinal, this is what we've got. And then if we combine sort of, so this would be braking in a straight line, and this should just be purely steering. And then if we do a combination of brake and steer, as it's sort of talked about in the trail phase, we get this arc, we get this sort of circle shape. So that's the amount of grip essentially a tyre has available. We can sort of map grip to acceleration. So we've got longitudinal acceleration, longitudinal and lateral acceleration. We can sort of equate to acceleration to equaling grip. So what we use is an XY graph and plot this lateral and longitudinal G. And if we go out and collect enough data, the chances are, if you're trying hard enough, at some point in the lap, you would have maximized the amount of tyre grip that you have available in one of the corners. As this just plots at any point throughout the lap, it's not lap specific, we quickly can build up our sort of our own, if you like, tyre friction grip circle. So then if we collect this data and work out roughly where our limits are, we can then consider the longitudinal and lateral G in isolation to a particular corner we want to look at. So generally, if you're analysing your driver performance, you'd look at your fastest lap, because that lap's your best at that given time, and then you look at ways to improving your best. So if you slowly move away through the data, if you move left to right in a time distance graph, the live plots would be moving around this circle. And if on your best lap you aren't getting close to this outer edge, this sort of your own generated circle, you could sort of safely say you haven't maximized the grip at that corner. I mean, it's not the be all and end all. There's plenty of ways errors can be introduced in here, but it's sort of the best we have with a relatively budget. Again, when I say budget, it's still GT3 level racing, basically not F1. This is sort of the best we can do with the tools we have available to us. So I wouldn't go out and risk your life on it, but it's a good indication that you weren't, if you're not close to the edge of that circle, there probably was more grip available to you. And then you look at whether it's predominantly under braking, whether it's trail phasing, whether it's acceleration, etc. You can then sort of work your way down alleys and narrow down exactly where your performance deficit is coming from. So all those techniques are looking at a lap of data in isolation. The thing what I do in GT racing, which is we're fortunate to have multiple team members, multiple drivers of the same car, is we can quite quickly speed up the driver performance analysis, data analysis, by comparing two different laps. So it doesn't have to be from two different drivers. It could be, as I mentioned before, yourself to yourself. So if you knew you'd done turn 3 better 2 laps before than your best lap, you could overlay that lap compared to your best lap and specifically look at turn 3. And what you can do there is visualize what you did differently. So we have a number of techniques to how we do this, but the most obvious one we have is using what's called a variance or a time diff mass channel, and I've got that, I can call it compare time. I've got this at the top here, and what this does is compare the time difference between the two laps you have. So the green lap is the green traces is 1 lap and the red traces is another. And what we look for is we make one of them the datum, and then we compare the other one to that. So in my Pi toolbox, the way I have my work that we looked at, when the green one is the datum, so when this time difference channel is increasing, so it's sloping up, that means the green lap, the fastest lap, is gaining time. And so if we zoom in on that, we can see that that's logical, that makes sense, because at this point in time, the green lap is carrying more speed. This is a speed trace, it has more speed, so it's going faster, and therefore less lap time than the red trace. That's an obvious one. I think that would probably, this is the braking zone, so it looks to me just quickly that the red trace has braked earlier than the green trace. That's why this time is being won by the green. And likewise, we can, the opposite is true. So when this line starts to slope, we go down to the speed trace and see that the red lap's actually gaining. And again, this looks like the red lap has carried a few more Ks through the corner and also picked the throttle up earlier as well. So we see down the next straight, the red lap is carrying more speed down the straight. So what we do is, I'll go to the next slide, is the way we calculate that is what we do is we look at the current distance throughout the lap and compare the lap's lap time at that point. So an example here is a fixed point on the track. So look at 1400 meters into the lap. Lap A has got a current lap time of 31.5 seconds, whereas lap B's got 31.85. So at that distance, lap A is 0.35 seconds faster. So that's all that line is doing, is plotting the difference in lap time. And again, it's just a really quick visual cue to work out where your most significant time won and loss is between 2 laps of data. And then you can focus in on those points using the techniques I've already mentioned in analysing a driver's performance in isolation. Just a note there is, again, you have to consider the whole sequence of that corner. So that's from the end of the previous straight before we started braking to the end of the following straight before we start braking for the next corner. Because again, it can be quite easily to go barreling into a corner way too fast. So momentarily you gain a load of time because your speed is high, but you compromise the corner, you compromise your corner exit. By the end of the next straight, you're actually down. So don't just look for a spike in time won or lost, time variance. Look for a gain that's made and doesn't diminish by the next corner. So yeah, I've realised I've gone on a bit there. I was trying to keep it quick, but I hope that's a benefit. I hope that's sort of introduced you to the world of driver data. I'm sure there'll be plenty of questions. I'll try and answer them. Yeah, I hope that's beneficial to you and you get some benefit of it and whets your appetite and makes you want to look further.
Thank you so much, Ben. You can have a slight breather while I look over these questions. So some of them were answered naturally through the presentation, but there's a few outstanding that I'll put to you. And forgive me if I get some of the terminology a little bit wrong, but I'll do my best. So we've got the first question is, hi Ben, when measuring your accelerations, how can you make sure that the accelerometers are in the right place? COG, for example.
That's a more complex question in its own, and it's probably beyond the scope of what this presentation is. Again, I would say this presentation is concentrated on driver performance. And using the 80-20 rule I discussed, it doesn't, as long as it's your acceleration sensor aren't moving in the car, so they're at a fixed position, you're generally, for driver performance, you just really want to know the trends. You want to know the shapes. You want to know whether it's increasing or decreasing. You don't, the actual value of what the sensor reads isn't massively important in terms of analysing driver performance. Yes, as you do more complex calculations, mounting it accurately and how you determine the C of G becomes a lot more significant. But as someone that's sort of the intended audience of this, of people that have never used driver data before or use any sort of data analysis before, you don't have to worry about being that accurate to still be able to productively use the results, if that makes sense. So the key thing there, though, with mounting is a good point, is to ensure that the accelerometer can't move. So and which would definitely induce erroneous values, and then you couldn't trust the trends, you couldn't trust the shapes. So I hope that makes sense.
Thank you. A question from Chris. Beside I/O limitations on the engine ECU, what other factors would drive my decision to use the ECU's internal logging versus a dash logger versus a data buddy type device without additional inputs, or standalone logger with its own additional input pin capability?
Okay, that's a good question. As I say, ECUs are probably the most common electronic device out of motorsport at the minute. They've been around a lot longer, been more prevalent than sort of the chassis side electronics. Fundamentally, it comes down to the supporting data analysis package. I've worked with a few like Life Racing and Cyvex, etc., where their whole data analysis software was developed for the purpose of helping an engine tuner and helping helping someone that predominantly looks at engines. So they won't have the necessarily, I'm not saying this, I haven't worked with Life or Cyvex, it's just an example, but if the software is built around purely analysing engine data, it won't have some of these features. So it won't have split reports, it won't have necessary track map graphs, and it won't be able to split the data into laps like you'd want it to. So that would be a consideration. But if you want a modern ECU, which is has a mature supporting data analysis software that's easy to work with, there's nothing stopping you use it. That'd be a great way to introduce yourself to it if you're confident at looking at engine parameters but you haven't yet looked at your own driver data. Then yeah, crack on. If you know your way around the analysis package and you can build a time distance graph like I looked at, that's a great way to get going, and it shouldn't cost you too much more money.
Perfect. You may have answered this one in the braking section, so if you have, we'll move on. On monitoring brake pressure, would you use two sensors if you have separate brake cylinder for front and back? So
again, yes. If your budget's there, that's what I do. All the professional customer cars do that. That's I would say it's a luxury if you've just got individual braking circuits, whereas if you also have adjustable brake bias, so you can move the balance between front and rear, I would then move that from luxury to essential, that you monitor both circuits. So it depends on your hardware setup, but yeah, good point. If you've got a twin circuit system front and rear, it'd be a great move to put a sensor in each circuit.
Great. Pippa asks, how can you verify that the GPS is picking up the correct position, or is it always quite accurate?
So this can be a tricky subject. GPS technology is improving sort of year on year, and if you've got a sort of 7 or 8 year old system now, it can be pretty flaky. But as the technology progresses, it becomes more and more reliable, more and more accurate. In terms of validating GPS, there's things now like Google Maps, etc., where it allows you to overlay. If you have a string of data in a text format, so you can have your GPS latitude and GPS longitude positions. Lots of good data analysis software allow you to export from their software into a text file, into an Excel document, which is just gives you a long list of numbers. Basically, input them into something like Google Maps, and it will draw the line for you, much like I showed with the XY graph with the driving line. It will essentially do the same thing for you, but over a map. So if those values don't line up to the actual track, if you look on Google Earth, etc., Google, then you could say you're not accurately measuring the GPS position. But if you've got something fairly modern, that hasn't been a recent worry of mine, put it that way.
Great. Chris asks, given that the front brakes do the bulk of the work, does having a high initial peak in the brake force in the first phase of braking not risk locking the wheels before the weight has transferred onto the front wheels?
This is a good point. More of the point of what I was trying to say is we expect to see a peak at this point and in the first phase, and the first phase should be where your highest pressure is seen because of the initial movement and the energies involved. But yes, there is always a point. It's not an unlimited value. You don't want to just get more as much as you can get. There will be a limiting factor, and brake blocking, just as in the mid phase, is just as important. Locking brakes and looking out for that, the signs of that in both wheel speeds or drops in deceleration, drops in longitudinal G, sorry. They're all important to look out for in both the first phase and the second phase. But the point I was trying to get across is this first phase is when we should see the peak, and that's where we should see the highest values throughout the braking phase.
Thanks, Ben. We've got a question from Toby. Should a brake trace differ between a high downforce and a GT or a touring car?
In terms of shape, no. That the general start high and drop off towards the end, you should still see that general trace. But the magnitudes will change quite differently. So when you're heavily aero dependent, you can the faster you go in, effectively the more grip you've got. So you're actually trying to you wouldn't be scrubbing off anywhere near as much speed towards the end of the braking phase as you would be with a GT car. So the magnitudes change, but in general, the shape should always be the same.
Thanks, Ben. We've got 3 more questions, and then I think we'll come to a close there. So if you're happy to take these final 3, Richard asks, I have a Radical RXC with life data system. Can I use the techniques you have covered, and is it possible to extract the data you have covered from the life data system to do this type of analysis?
As far as I mean, I don't know. Some manufacturers have agreements. So Radical would have an agreement with the data electronics provider to lock down their systems. That's quite common. I know Porsche do that a lot. I haven't actually worked with a Radical, so I can't say for sure. So it is popular that manufacturers lock down their calibration files because of how much time they've spent developing it. If your system is open, there's nothing stopping you wiring in additional sensors. I mean, it might be practically tricky if your loom's all sealed and it's hard to add wires, but I don't see why you couldn't add sensors that aren't already there. I mean, lots of these things, Radical are an established track car company. I'm sure they probably would have already included much of these sensors. So it'll probably already live in your your log data file, and it's just a matter of picking them and adding them to your time distance display to get yourself started.
Cool. Graham says some driver coaches use key performance indicators derived from data logging to measure driver performance. What are your views on this approach as opposed to looking at data shapes?
I mean, you have to consider the driver's level and where they're at before you start, how consistent they are. I've also seen which there's some devices now which have sort of key performance indicators built into them. You get a set of flashing lights to try and tell you where your limits are. In practice, like generally that sounds like a good idea, and I think the majority of cases that's fine. But I also think you have to look at the data where you develop these KPIs. Yeah, you have to look at the sequence of the data where you develop the KPI to work out how valid it is. Like I say, it's easy to go absolutely barreling into a corner way faster than you would to gain a good lap time, which would have a massively high peak corner speed, entry speed, and you'll be generating all this combined G. Your G measures be through the roof, and you could come back and say, yeah, I've done this, or I've done that, but in practice that was no good for your lap time. That was you're sort of you're going after the KPI rather than actually using the KPI to go faster, if that makes sense. So it depends what KPI they use. I assume that KPI stands for sort of key performance indicator, as it does in other sports and stuff. So yes, there's metrics you can put on these things, and I use one called coast time, which is I have a little counter that counts up when the driver does. So the transition between the driver should be accelerating and then almost simultaneously coming off the accelerator and applying the brake. So if there's a big gap, which I call coasting, there's no sort of hard and fast term, but it's common to see a driver lift off the throttle pedal, do nothing, and then they get on the brake pedal. I call that coast time. That's time where you're not doing anything practical with, and it's essentially wasted time. So I have metrics to count that, etc. So yeah, they are good, but my only sort of worry with that is you can easily go after just trying to beat a metric, but that won't have the greater impact of improving a driver's performance on a lap, if that makes sense.
Okay, and question from Daniel. Would you also be able to plot external aero pressure traces within the mechanical traces, e.g. vehicle speed, to potentially give reason behind a sudden loss of grip that may not be mechanically based?
Yeah. I mean, so we're getting into the more in-depth data analysis, and so it's a whole another world out there. It's probably beyond the scope of this presentation, but yes, he's right. You can start logging all sorts of aero factors, and the more things you log, the more crazy you can get with your mass channels, and it sort of exponentially grows. But you got to start somewhere, and hopefully this is a way of whetting people's appetite. Is the squiggly lines on, if you're not, especially I know plenty of people from my engine building days which are very practical people. They're hugely talented, but squiggly lines on a laptop scares them, and I hope this is sort of a introduction to converting those people. It's not quite as scary, it's not quite as difficult, and it can, I think mechanically rather than electronically, etc. And it makes sense to me, so I hope that would show it makes sense to them and it's something they could work with. So yeah, good question, but probably beyond the scope of this presentation.
No problem. Chris has asked if we're able to fit one more question in, so we'll finish on this one. Does the rule of not getting on the throttle until you wind off steering lock still apply to a loose surface where diff load comes into play?
That's a good question. Yes, so the rules of thumb put into this document are more to do with circuit racing. I have to admit, I'm not massively educated, not an expert on sort of rallycross or rallying, but what he says makes sense of engaging a differential, especially in a loose surface. So I wouldn't be more analysis needed from my side and more data collection as to whether that is actually beneficial or not. But it doesn't sound wrong in the context of loading up diffs on a loose surface. So yeah, I'll have to say, fortunately, my experience is all tarmac and circuit racing based. So good question.
Great. Okay, well, we'll finish the questions there. Thank you so much, Ben, for taking the time to do that. I hope everybody found that really insightful and valuable, and you can apply some of those principles to your own performances and your own disciplines. If you enjoyed the session and would like to know more from Ben, please do get in touch using the contact details on the screen. During the off season, Ben's able to offer some opportunities and services, which he's listed on the right hand side there. So, you know, opportunities for race teams, engineers, aspiring data analysts. Ben also has a new website on the horizon, so keep an eye out for updates on that in the near future. Thanks again, and enjoy the rest of your evening, everybody.
Thank you very much.
Thank you. Bye.